This presentation is the third of three presentations on calculating and interpreting a z-test. In this presentation, we will learn how to interpret the results of the z-test. Let's look over the results for a z-test calculation from our previous presentation. Recall that the z-test result ended up being 0.65. What does this calculation mean? To interpret the result, and thus come to a conclusion about the null hypothesis, we need to turn to page 143 in the Pollock 1 textbook. This page is headed by Table 6.3, Proportions of the normal curve above the absolute value of z. This table tells us what percentage of observations lie above the absolute value of our z-test calculation. To create an absolute value of any number, simply make the number be a positive number. So our z-test result of minus 0.65 in absolute terms is 0.65. What percentage of observations lie above 0.65? To use Table 6.3 correctly, look at the column on the far left of the table, headed by first digit and first decimal of z. The first digit of our z-test result is 6, so proceed down to 0.6. We then need to consider which column is correct to go to under the heading second decimal of z. For our z-test result, the correct column is 0.05, since our z-test calculation in absolute terms is 0.65. Thus, the percentage of observations that lie above the calculated absolute z-test value is 25.78, which is the result when we make a percentage out of a decimal, moving the decimal point 2 places to the right. Let's re-examine the normal curve on page 139 of the Pollock 1 textbook. You can see that 25.78% of observations would put the z-test result, and thus the difference between the sample mean and the population mean, standardized by the population standard deviation, pretty close to 0. In other words, that is a very common difference and is very close to 0, all things considered. We're not seeing anything very special in the difference in mean absentee rate between the vocational training students and the high school population. But we need a more specific judge of not seeing anything special. We need a standard, thus, for special. That standard is found on page 139, where we see the arrow pointing to z equals 2, with the arrow labeled 2.5%. By agreement among social scientists, this is the point at which we make our decision to accept or reject the null hypothesis. In other words, any percentage of observations that lie above the z-test result of 2 in absolute terms is a rare enough percentage to be called very special. To return to the table on page 143, notice that there is one proportion on the table that is in bold type. It is 0.0250. In percentage terms, it is 2.5%. Any percentage that is 2.5% or lower indicates a very special z-test. We will accept the null hypothesis, notated as H sub O, that there is no statistically significant difference between the mean absentee rate for the vocational training students, the sample mean, and the mean absentee rate for all of the students in the local school district, the population mean. And we will accept the alternative hypothesis, notated as H sub A, that there is a statistically significant difference between the mean absentee rate for the vocational training students, the sample mean, and the mean absentee rate for all of the students in the local school district, the population mean. In mathematical terms, the percentage of the normal curve above the absolute value of the z-test is equal to 0.2578, which is equal to 25.78%, and we accept the null hypothesis because 0.2578 is greater than 0.0250, and we reject the alternative hypothesis. In practical terms, the students in the vocational training class are absent less frequently than the students at the high school on the whole, but they are not statistically significantly less absent. There's a difference, but it's not large enough for it to be considered statistically meaningful. This concludes our three-part presentation of the z-test.